Okay, we're back with part 2 of the derivatives of the inverse trigonometric functions. Yesterday I gave you the formulas right here on your packet for the 6 inverse trig derivatives, and we did some examples, and you ended up doing your homework, which was over here on this page. We did number 6 down here together, and then you did 15 problems and checked them out on the answer key. Today, we're going to focus on the second page of the packet, which I saved. This page is going to show us why the first formula is what it is. I have chosen to prove only the first formula. We're going to prove why the derivative of sine inverse of x is what it is. And the other 5, you're going to take my word for it. So before I start this proof, I want to do a mini lesson on inverses, because if you don't remember what an inverse function is, it's going to make this proof really difficult to understand. So I picked a linear function, something really simple. Let's look at this. So I have y equals 4x plus 4. And although I know you could graph that by going to 4 on the y-axis as your y-intercept and then using your slope of 4 over 1, I chose to make a table. So I chose the x values -3, -2, -1, 0, and 1, and I fed those into x to get the corresponding y values here. And you can see when x is -3, 4 times -3 is -12, plus 4 is -8. So that's where those are coming from. And I plotted those points over here, and you can see the y-intercept is 4, and the slope is up 4, right 1, so there's your line. Now, the definition of an inverse, we're going to come down here. The definition of an inverse is to switch the x and the y. So I took y equals 4x plus 4 and switched it to x equals 4y plus 4. This definitely is the inverse of the function, but it's kind of awkward because it's solved for x and not y. So I'm going to take this inverse and go ahead and solve for y. So I'm going to subtract this 4 over to the left side, which would give me x minus 4 equals 4y. And then to get y alone, I'll divide each term by 4, which will result in a final answer of y equals 1/4 x minus 1. This is also the inverse of our function. So two different forms of the equation. One solved for x, one solved for y. Now, if you look over here, what I did here is I took this original table and I flip-flopped it. If I'm switching x and y, then the y's become the x's and the x's become the y's. So I'm going to go ahead and plot these points and take a look at what this looks like. So -8, -3 be right here. -4, -2, 0, -1, 4, 0, and 8, 1. So if I draw that line, that's going to represent the inverse. And I'm hoping that from your prior math studies, you remember that when you graph two inverses, they will be mirror images across the line y equals x. So if I graph the line y equals x right here, these lines should look like a mirror image across that line. So that's just a mini lesson on inverses. Now, I'm going to take that mini lesson and apply it to the proof that we're going to work on today, which is the inverse sine. So, let's take a look at this. We're going to start with y equals sine x. I graphed it right here. We've studied this before. The graph of y equals sine x, 2 cycles of it, is going to look like this, sort of that S shape coming around here. I made a table to represent y equals sine x. You can see at -2 pi, I'm at 0. At -3 pi over 2, I'm at 1, etc. -pi 0, all the way down to 2 pi. So, if I have y equals sine x, then its inverse, if we switch x and y, would be x equals sine y. Now this is definitely the inverse of y equals sine x. But we can also solve it for y. So if you solve it for y, it's going to look like this. Y equals inverse sine of x. Now, if I flip-flop these values, I will get my graph. So instead of going to -2 pi 0, I'm going to go to 0, -2 pi. Instead of going to -3 pi over 2, 1, I'm going to go to 1, negative 3 pi over 2. So this creates this sort of S shape coming up and winding around the y-axis. Now what's interesting is this is not a function. If you would draw a vertical line right here, my goodness, it would hit the graph over and over and over again if we kept going. So this is not a function. So we define inverse sine of x to be a function only between the y values of negative pi over 2 and positive pi over 2. And that's because we take this portion right here of the graph, closest to the origin and remaining a function. If we go any higher than pi over 2 on the y-axis, if we turn that bend, we fail the vertical line test. If we go any lower than negative pi over 2, if we turn that bend, we fail the vertical line test. So y equals sine inverse x is defined only right here. If you look at those values on the unit circle, that means you're only defined, starting here on the right, at 0 radians. Negative pi over 2 would be down here. Positive pi over 2 would be up here. So we're trapped on the unit circle for the inverse sine function on the right side of the circle. And this is going to come into play in our proof. I want you to note that the cosine on this half of the circle is always positive. The cosine, if you were coming to the right and up, your cosine is positive. If you were coming to the right and down, your cosine remains positive. So keep that in mind as we move forward. Okay, so page 2 of the packet from yesterday is going to reiterate what I just went over. Here are your 2 cycles of the graph of y equals sine x, as I showed earlier. This next picture shows the graph of y equals inverse sine of x, but I'm only showing, once again, that part that is a function right here, which is defined only for y values between negative pi over 2 and pi over 2. Okay? So I'm going to actually recreate that unit circle I just drew. So keep in mind as we do this proof, we are trapped on this half of the unit circle. Okay. So here comes our proof. We're going to start with y equals sine x. Now let's not forget, we already know the derivative of y equals sine x. If I was finding the derivative of y equals sine x, it would be y prime equals cosine x. Simple. But now, I want to go a different direction. I want to find the derivative of the inverse of sine x. So I'm going to flip-flop my x and my y, which is going to give me x equals sine y. This is the inverse sine function. So if I can find the derivative of this, I've got my formula. Well, I can find the derivative of this. Since I know that the derivative of sine x is cosine x, I know that the derivative of sine y is cosine y. And if I use implicit differentiation, since y is not solved for, I should have my magic. So let's implicitly differentiate the inverse sine. The derivative of x is 1. The derivative of sine y is cosine y dy dx. Solving for dy dx, I'll divide both sides by cosine y, and this will give me dy dx equals 1 over cosine y. Truly, that is the derivative. But if you look at the formulas on the front page, this isn't what I wrote. We're not satisfied with our derivative having the cosine function in it. So we're going to try to get rid of the cosine y and rewrite cosine y a little bit differently. So what we're going to do, and this is going to seem a little odd, it's going to seem like we're going off on a little bit of a tangent here. We're going to actually remember the Pythagorean identity that we studied earlier this year. The Pythagorean identity says that sine squared y plus cosine squared y equals 1. I'm going to solve this for cosine squared y because I'm trying to rewrite cosine y a different way. So if I subtract sine squared y from both sides, I'm going to have cosine squared y equals 1 minus sine squared y. Now that's getting close, but now if I square root both sides, I'm going to get cosine y equals plus or minus the square root of 1 minus sine squared y. Now, here's why I was getting so into this unit circle earlier. I'm going to throw out the negative square root because the cosine y is always positive for where the inverse sine function is defined. So I'm going to rewrite this as cosine y equals the positive square root only of 1 minus sine squared y. Now, if you look back right here, sine y is equal to x. Therefore, I can write this as cosine y equals the square root of 1 minus x squared. Sine y squared is like sine y quantity squared, which is the same as x squared. So, if I come back to my dy dx here, instead of writing dy dx as 1 over cosine y, I'm going to rewrite it as 1 over the square root of 1 minus x squared. And if you look at your front page, you will see that if you take the derivative, let's go back here, of y equals sine inverse of u, in this case it's an x, the derivative is 1 over the square root of 1 minus u squared times the derivative of u, which is 1 over the square root of 1 minus x squared. So whether you use the formula from page 1 or the proof that we just did, you're going to get the same answer. So that is the reason why that formula works. That's the only one I'm going to prove, and this will end this video.